Hi, welcome to Chemistry Home Instruction, week 6.4. Today we're going to talk about Dalton's law of partial pressures and the ideal gas law. For Dalton's law of partial pressures, John Dalton came up with this in 1801. It also relates to the ideal gas law, which we'll talk about in a moment. This tells us that in a mixture of non-reacting gases, your total pressure is going to be equal to all of the pressures added up together. So it's a very simple equation, very simple concept. Your total pressure equals all of the pressures of the individual gases added together. Sometimes you can collect gas underwater. So if you look at the image here, we have a Bunsen burner that is heating up some potassium chlorate, and then it's creating a oxygen gas bubble that's going down this tube and into a container that was filled with water. And it's replacing the water with the oxygen gas. Whenever you are considering the total pressure in this case, your total pressure is going to be the pressure of the gas that you're collecting, but it's also including the pressure of the water vapor that's coming off of the surface here. So your equation is going to be the total pressure is equal to the pressure of the water plus the pressure of the gas. Now, a lot of times we refer to the total pressure as the atmospheric pressure or the barometric pressure. Okay, so if we do say barometric pressure or atmospheric pressure, that means total pressure. All right, let's do an example. We have a container that has 3 gases. Okay, it doesn't say anything about collecting the gas underwater. That's how you know you're going to use this equation right here. The total pressure equals the individual pressures added together. So you have the pressure of the oxygen gas, the carbon dioxide gas, and the helium. Okay, so here's their pressures, 2, 3, and 4. Do the pressure units match? Yes. Okay, so that's good. We can go ahead and plug all of them into our equation and solve. We don't have to do a pressure conversion here. What is the total pressure in the container? Well, you just add up the individual pressures. 2 plus 3 plus 4 gives you 9. So it is that simple. All right, now here's an example whenever the gas is collected underwater. So the gas is collected by water displacement. Whenever you see something like that, you know that you're going to use the equation total pressure equals pressure of water plus the pressure of the gas. Okay. It tells us that it is at 50 degrees Celsius. Okay, so at that temperature, the water vapor pressure is 12.3 kPa. Okay, so our pressure of our water, 12.3. The barometric pressure is 95. Okay, so remember, barometric pressure is total pressure, and we are looking for the pressure of the gas. So first of all, do our pressure units match? Yes, they are both in kPa. That's great. You can go ahead and plug them in without having to convert one to the other. They're the same. So we're going to use our equation. Total pressure is the pressure of the water plus the pressure of the gas. Plug in your numbers. So we know here that whatever pressure this gas is, when you add it to 12.3, it has to equal 95. We can rearrange the equation and just subtract. So 95 minus 12.3 gives you 82.7 kPa. Okay, now let's talk about the ideal gas law. The ideal gas law describes the behavior of an ideal gas, which is not real, but the equation is applicable to real gases under a lot of conditions, so it's useful for us to know. Our ideal gas law equation is PV equals nRT, where P stands for pressure, V is volume, N is the number of moles, R is the ideal gas constant, and T is the temperature in Kelvin. So for pressure can be in whatever units they give you. Volume has to be in liters. If they give you milliliters, divide by 1,000 and put it into liters first. Then you can plug it in. N is the number of moles. So that does have to be in moles. Say, for instance, you're given grams. You would have to change that into moles first and then use it in the equation. And the ideal gas constant is a constant number. That means that it's always going to be one of these 3 numbers. Okay. Now, how do you know which one of these to pick? Okay, you're going to choose the R that matches the units for pressure. So go back over here and check whatever units you had for your pressure. If your pressure is in ATM, you're going to use 0.0821. If your pressure was in millimeters of mercury, you're going to use 62.4. If your pressure is in kPa, you're going to use 8.31 for your R constant. And then for our temperature, it has to be in Kelvin, like always with gases. So if you are given Celsius, make sure that you add the number 273 to get it in Kelvin. Now, here are your equations for pressure, volume, number of moles, and temperature, depending on what you're asked to solve for. Okay, here is our first example for the ideal gas law. We're going to write out PV in our T and fill in our variables as we read the problem. So what will be the volume, right? That means that we are looking for volume in this case. So that's our question mark. We have 0.1561 moles. So under N, we're going to label it as 0.1561 moles of SO2 gas at 35 degrees Celsius. Now, remember, your 35 degrees Celsius cannot stay as Celsius because the temperature is in Celsius. We have to add 273 to get it into Kelvin. So we're going to use the temperature of 308 Kelvin instead of 35 degrees Celsius. And then it says our pressure is 740 millimeters of mercury. Okay, so we're going to go ahead and plug that in to pressure. It is important to pay attention to our pressure units. Okay, because our pressure is in millimeters of mercury, we're going to choose an R constant of 62.4. Okay, because it can only be one of those three options from the last slide. So now that we have all of our variables filled in, we need to solve for volume. So we're going to use our equation. Volume is equal to moles times the R constant times the temperature in Kelvin divided by pressure. Plug in all of your numbers and solve. Remember that volume is going to have the units of liters because the ideal gas law always uses liters for volume. All right, example 2 for ideal gas law. We will have our variables PV and RT and fill them in as we read the question. So we have 0.9995 moles, and that's going to be our N. Nitrogen gas, and it's sealed in a 6-liter container. Liters is volume. Okay, and it's already in liters, so we don't have to change anything there. It's heated to a temperature of 327 degrees Celsius. Because temperature is in Celsius, we have to add 273. So we're going to use a temperature of 600 Kelvin. What is the pressure in kPa? Okay, so we have to know our units for pressure because that determines which R constant we're going to choose. And because pressure is in kPa, we're going to choose an R constant of 8.31. Now we are looking for pressure. So we're going to use our equation for pressure equals nRT divided by V. Plug in your numbers and solve. Now our third example and our last example, we start with 22,400 liters of propane gas, so that's our volume right here. It says the gas is at 0.95 atm. Well, by this point, you should know that atm is a pressure. Okay, so that's going to be labeled right there. We have 15 degrees Celsius. Celsius needs to be converted into Kelvin, so we add 273 to that and get 288 Kelvin. So they're going to take this huge amount of gas and compress it and put it into a barbecue grill tank. How many moles are inside the container? We're looking for N, the number of moles. Because our pressure is in atm, we're going to use our R constant of 0.0821. Okay, now that we have all of our variables, we're going to go ahead and plug it into the equation. N equals PV divided by RT. Now in your calculator, you have to put the parentheses around the pressure and the volume being multiplied together, and then put the parentheses around the R constant and the temperature being multiplied together. This tells the calculator the order of operations. It tells it to multiply this section first and multiply this section second, and then go ahead and divide those two numbers. So once you plug it in, you get your number of moles. Okay? So that's all the examples we have for you today. I hope it helped, and we'll see you next week. Thanks. Bye-bye.